this video, we'll see how to use R's numerical optimization techniques. Numerical optimization is a way of optimizing a particular function, usually maximizing the function, for a given set of parameters. The example that we'll use is the log likelihood function of the Poisson distribution. This is the function that gets maximized through maximum likelihood estimation when estimating Poisson regression models. The first step with numerical optimization in R is to create the actual function to get optimized. I'm going to name my function ll.poisson for log likelihood Poisson. And there are three different arguments that this function is going to take. First one I'm calling PAR, that's the parameters, and in this case it's going to be the coefficients of the Poisson regression model. The second argument is going to be y, which is going to be the dependent variable. And then I've got an object called x, which can be a single independent variable or a matrix of independent variables. Then you'll notice I have my curly brace here, and so everything inside the curly braces is going to be the actual function. First thing I'm going to create is an object called lambda, and this is inside the function. Lambda is the parameter of the Poisson distribution, the mean or the expected number of counts. And the theory of generalized linear models tells us that the canonical length function, or mean function in this case for the Poisson distribution, is to exponentiate the linear predictor. That is, take the independent variables times the coefficients and exponentiate that. That forms the linear predictor. We exponentiate that linear predictor to get lambda, which is the expected count parameter in the Poisson distribution. Now the next step, once we have that parameter, is to compute the log likelihood. I've got three different ways of doing that in these next three lines, and I've got two of them commented out. The first one in this function is the expression for the likelihood function right here with the log command wrapped around it and the sum command wrapped around that. So this is the likelihood function of the Poisson distribution, taking the log of it and using the sum command to add that up, because it's much easier to work with the log of the likelihood rather than the actual likelihood. So that's one option. The second option is to write the expression directly for the log of the likelihood and then use the sum command. So that's what I'm doing in the second line. And then probably the easiest of all is just to use R's dpois command. This dpois command, D-P-O-I-S, is the command used to work with the PDF, or the density function, or the probability mass function, more specifically, for the Poisson distribution. I've got dependent variable y, I've got the parameter lambda, and then I've got log equals true, because again we're working with the log likelihood. And then I'm using the sum command to sum that up, because dpois computes the probability of each observation given lambda and logs it, and we want to add all of those up to produce the value of the log likelihood. And then the last command in this function is the return command. So this function takes a set of parameters, or betas, the coefficient estimates. It takes dependent variable, independent variables, it computes the log likelihood and spits that out. I've got three different ways of computing the log likelihood here. They all produce the same numbers. It's just three different ways of doing it. I think this third way is the easiest. So I'll go ahead and run that. And the next step in this example is to generate some data where we have knowledge of the true relationship. And that way we can see if, when we optimize the function, we get numbers that look like the true numbers that we created. So I'm going to start by setting the seed. You might remember that by setting the seed we can reproduce the same random numbers each time. I'm going to set the object n, which is the sample size, to 1,000, and I'm going to create two independent variables, x1 and x2, which are just 1,000 random draws from a uniform distribution. Now here's where I'm actually going to create the true coefficient parameters of this model. I'm going to set this object A, which is the intercept, equal to 1. I'm going to set beta 1 or B1 to 0.5 and B2 to 0.25. Then I'm going to create an object called linear.predictor. That is alpha plus beta 1 times x1 plus beta 2 times x2. So this is just a linear combination of the parameters and the independent variables. Now this next line is real key. This is the actual data generating process unfolding in the dependent variable. So I'm creating the object y as a random draw from a Poisson distribution. That's with the rpos command. I'm going to do 1,000 of these draws, and I'm going to set lambda, the parameter of the Poisson distribution, equal to the exponentiated linear predictor. So in doing that, I've now created y, the dependent variable, as a set of count values that are driven by or influenced by the linear predictor that we set here, but still have a random or stochastic component. And so now we can do Poisson regression of y on x1 and x2. First way we're going to do that is with our own maximum likelihood estimator that we use with an optimization function in R. The function itself is called optim, O-P-T-I-M. We need to feed it starting values, the data, and the function that we want to optimize. So remember, the parameters we're trying to optimize are the three coefficients in this regression model: intercept, beta 1, beta 2. I'm going to create an object called start values that is just 3 zeros. So I'm going to start the numerical optimizer at 0 for all three of those parameters. So the argument PAR is what Optim is expecting for start values. Then I've got y equals y and x equals c bind 1, x1, x2. These are the parameters of the actual function that we're optimizing. So if you recall up here, when we created our Poisson likelihood function, there's an object called y and there's an argument called x. We see those repeated down here. The argument y that goes into this function, I'm setting equal to this dependent variable that we just created. And this argument x that the Poisson likelihood needs is going to be a matrix of 1s, x1, and x2 in 3 respective columns. The matrix of 1s represents the intercept, x1 is the first independent variable, x2 is the second one. Next up, there's an argument called fn, that stands for function. That's telling R which function we should optimize. Then I've got method equals BFGS. This is the particular algorithm that's going to be used to optimize the function. I'm setting Hessian to true to compute the numerical Hessian. That's going to allow us to get standard errors. And then finally, there's this last bit of code. Control equals list, fn scale equals -1. By default, the optim function in R is a minimizer. And so this last bit of code is needed to make the function a maximizer. So I'm going to run my start values. And just to get a sense of what that Poisson likelihood function is doing, let's just run that function. So not worrying about optim at this point, but just running that function. I'm going to type ll.Poisson. For my parameters, I'm just going to put in the start values. Then I'm going to put in my dependent variable y and my matrix of x variables. And what we get is the value of the log likelihood for the Poisson model, given those data, at the parameters 0, 0, and 0. Now, let's say we wanted to change that up a little bit. Let's say instead of those start values, we wanted to try 0.2, 0.3, 0.4. This is just another set of possible values. We could do the exact same function again with those parameters, and now we get this value for the log likelihood. Notice that it increased from the first value. So this set of parameters has a higher relative likelihood of generating the data that we have in our hand compared to the start values. We could keep doing this over and over, guessing another set of 3 numbers to see which combination produces the largest value for the log likelihood, or we could just use optim to numerically find the set of estimates that produces the highest log likelihood. So that's what we're doing here. I'm going to create an object called poisson.model that is this call to optim. And when we run that, here's what we get. We get a list of results. The first one is PAR. Those are the parameters. So notice that our estimate for the intercept is 0.9984648. For beta 1, it's 0.5239003, and for beta 2, it's 0.3327872. Remember, we set the true values over here to 1, 0.5, and 0.25. In this sample of data that we generated right here, these are the parameters that maximize that log likelihood. They're pretty close to the true values, but they're a little different from what we set because of the randomness of just drawing a sample. So those are the parameters that we just estimated. Those are the combination of 3 estimates that maximize the log likelihood as we were doing up here. This is the actual value of the log likelihood. So we can compare this value right here to these 2 numbers that we computed with our own guesses. Notice that's that number is larger than either of these 2. Here's some other information about the function, and down here we've got this object called Hessian. This is the numerical Hessian matrix. We can pretty easily get standard errors out of this. So over here I'm going to create another object called poisson.cov. That is the Poisson covariance matrix. And if you recall from maximum likelihood, we get the covariance matrix out of the Hessian by inverting the negative of the Hessian. So that's what this code is doing here. The solve function does the inverse. I've got a negative sign here. That will produce my variance covariance matrix. And I can print that out. And here we have the variance covariance matrix. Now the standard errors come from the square root of the diagonal, the main diagonal of this matrix. So that's what I'm doing here. And then we can compute z statistic for each coefficient. Once we have the coefficient estimate and the standard error, that's what I'm creating here. And we can even create p-values with the pnorm command. Then I can put those results together with the cbind command and display them with rounded to 3 digits so they're a little bit easier to work with. And here's what we get. First column is our coefficient estimates, 0.998, 0.524, 0.333. Standard errors are right here. Z values here, and our p values are very small. All, when rounded to 3 digits, come out to 0. Now, just to be on the safe side, let's check these results with R's GLM function. So the GLM function we saw with the logit model, if we say family equals Poisson, it's going to estimate a Poisson model. So I'm going to create this object called check.model and summarize that to make sure the results are the same as what we got with optim. So run that, and then the summary command, and here's what we get. For the intercept, an estimate of 0.998, x1 0.523, x2 0.332, all pretty close to what we got. And also the standard errors and the z statistics and the p-values are all very close to each other as well. Now they're not quite the same. If you look at the results from Optim out to several digits and you look at these, you're going to see minor differences, and that's likely due to the fact that we had to pick particular start values for our function, and the GLM command didn't necessarily pick those start values. But for all practical purposes, we can see that our Optim function is finding the same maximum of the log likelihood that this GLM command is finding. So this is just one example of how to use Optim. It's a very flexible command. You can feed it any function that you can create and maximize or minimize that function. So it's a very useful tool to have, especially if you're programming your own type of estimator in R.